Welcome to The Explainer, where we, you guessed it, break down the big topics.
Okay, think about this for a second. You live in a city of giants. You're surrounded by these massive skyscrapers, bridges, tunnels. But how often do you actually stop and think about what's keeping it all from, falling down? Today, we're pulling back the curtain on the hidden world of civil engineering tests that keep us safe every single day.
And to really get our heads around this, we're going to go on a little journey. We're going to build a structure, right here, one tested piece at a time. This way, we can reveal the incredible and often invisible science that literally holds our world up.
All right, first things first. We have to start at the very, very beginning, with the humble brick. You might think a brick is just a brick, but before it ever gets near a construction site, it has to prove it's tough enough for the job.
And what's so cool about this is just how low-tech but super effective these first checks are. These are field tests, stuff you can do right on site. You clink two bricks together. A good one will have a nice, sharp, metallic ring. Then you try to scratch it with your fingernail. If you can't leave a mark, that's a good sign of its hardness. And finally, the drop test. If it can survive a fall from about 1 meter high, it's got the toughness it needs.
Okay, so after the field test, it's time for the lab. And this one is crucial. A top-quality brick gets soaked in water for a full 24 hours. When you take it out, it shouldn't have absorbed more than 20% of its own weight in water. Why does that matter? Well, think about it. A brick that acts like a sponge is a recipe for disaster. Moisture gets in, it freezes, it expands, and over time, it'll just crumble the structure.
Now, when it comes to the stones used in building, hardness is king, and we measure it using something called the Mohs scale. It's this really elegant concept that just ranks materials based on a simple question: what can scratch what? All the way down at 1, you have talc, which is so soft you can scratch it with your fingernail. And at the top, a perfect 10, you have diamond. Obviously, a good building stone needs to be way up there on the scale to resist all that wear and tear. All right, we've got our super strong bricks and stones, but they're not going to stack themselves, right? We need the super glue of construction, cement. And just like our bricks, not all cement is created equal. It needs a serious checkup before it can be trusted to hold everything together. And this is absolutely critical. We need our cement to be stable. This soundness test makes sure of that. See, if there's too much of certain chemicals in the cement, it can continue to expand, slowly, for years after it's hardened. It's like a self-destruct mechanism that creates pressure from the inside, literally cracking the concrete apart. This test prevents that long-term catastrophe.
And with cement, timing is everything. It's a race against the clock, but a very specific one. First, the initial setting time has to be more than 30 minutes. That gives the crew a workable window to mix the concrete, transport it, and pour it into place. But then, the final setting time has to be less than 10 hours. That way, it hardens fast enough for construction to continue without huge delays. It's a really delicate balance.
Okay, bricks, check. Cement, check. Now let's combine them with water and aggregates. That's just stuff like sand and gravel, to make the most used man-made material on the entire planet, concrete. But getting that recipe just right is both a science and an art.
So before concrete even hardens, the name of the game is workability. And the cake batter analogy here is just perfect. If it's too thick and stiff, you can't get it to flow into all the nooks and crannies of the mold. But if it's too thin and soupy, the heavy gravel will sink and the water will rise to the top. That's called segregation, and it creates massive weak spots.
So how do you measure this on a busy construction site? With another brilliantly simple tool, the Slump test. You basically pack fresh concrete into the special cone, tamping it down in layers. Then you carefully lift the cone off, and you measure how much the pile of concrete sags or slumps. The bigger the slump, the more workable the concrete is. It's a quick, easy check to make sure the consistency is perfect. And let's not forget the unsung heroes of concrete, the aggregates, the rocks and sand. They make up most of the volume, and they have to be incredibly tough, especially in things like roads. So they get put through the ringer. They're crushed, they're hit with sudden impacts, and they're worn down to make sure they won't crumble, shatter, or just wear away under decades of heavy traffic.
So here's the deal with concrete. It's a beast when you try to crush it. That's called compression. But try to pull it apart. That's tension, and it's actually pretty weak. The solution? We give it a skeleton. A skeleton of steel reinforcing bars, or rebar. This combo of concrete and steel is what makes all of modern architecture possible. To figure out just how tough this steel is, engineers do something pretty dramatic. They put a sample in a machine and pull it apart until it snaps. And what happens tells a story in 4 acts. Act 1, the stretch.
At first, the steel acts like a super stiff rubber band. It stretches, but if you let go, it snaps right back to its original length. But then you keep pulling, and you hit it. The yield point. This is the point of no return. The stretch is now permanent. Even if you release the force, the steel bar is forever changed, permanently longer than it was before. This is where it's officially damaged.
And here's the wild part. Just when you think it's about to give up, the steel actually gets stronger. It's a process called strain hardening, where the internal structure of the metal literally realigns itself to resist the pull. It's putting up one last, incredible fight.
But everything has its limits. It hits its absolute peak, its ultimate strength, and then the end begins. A weak spot appears, and the bar starts to get thin in the middle. They call it necking, before it finally dramatically fractures and breaks. And that whole epic struggle we just saw, that demonstrates a property called ductility. And honestly, it might be the most important, life-saving feature in all of construction. It means steel doesn't just snap without warning. No, it stretches, it bends, it deforms. It gives you visible signs like cracks and sagging, a clear warning that something is wrong long before a total collapse. It gives people time to get out.
All right, our building is standing tall. We've tested every single component along the way. But how do we give it a checkup now that it's all put together without, smashing holes in it?
The answer is non-destructive testing, or NDT. It's pretty much exactly what it sounds like. Clever ways to see inside the structure without destroying it. You can think of it like giving the building an X-ray or an ultrasound to check on its health.
And here are two really common methods. First, you've got the rebound hammer. It's this cool little spring-loaded hammer that taps the surface and measures the rebound to give you a quick idea of the concrete's hardness. Then, for a deeper look, you've got the ultrasonic pulse test. This is some high-tech stuff. It sends a sound wave through the concrete. The faster that wave travels, the denser and stronger the concrete is. A slow wave could mean there are dangerous cracks or voids hidden inside.
So what's the big takeaway here? The cities we live in, the bridges we cross, the buildings we work in, none of this is standing by chance or by luck. It's all held up by an invisible shield of constant, rigorous scientific testing every single step of the way.
So the next time you're walking through the city, just think about it. From the simple clink of two bricks to the high-tech echo of an ultrasonic pulse, you're surrounded by the results of this unseen science that makes our modern world possible. So, what other invisible systems that run our world should we explore next?
I hit the street now, same old grind, finding rhythm in the concrete.